It's our 17th lecture of Principal Methods and Applications of Nuclear Tracks. And in this lecture, we have to discuss furthermore about, we have to continue our lecture number 16, which we left in our previous video. If you forgot to watch that video, first go through that video, then move on towards this video. In this video, we will discuss about the factors affecting the saturation current. Okay. So what is basically, so as you know that when we apply the potential, as the applied potential increases, the ion pair produced inside the material also got maximum. Okay, so by increasing the amount of external voltage, you can produce more ion pairs. Okay, so more ion pairs being produced, okay, becoming low at saturation point. Understood? More, as you can see that as more ion pairs becoming low, so there is a point which is so called as the saturation point. Okay, so at saturation point your more ion pairs becoming low. Okay, let us clarify that several factors can detract from reaching saturation current in an ion chamber. Okay, the most important of these is recombination, which we already covered, which is minimized by ensuring that a large value of electric field exists everywhere within the ion chamber volume. Okay, because you know that ion chamber which has a number of gas molecules inside, and when we apply external potential, external voltage to the gas chamber, the ion pair produced inside the chamber volume. Okay, and thus such as alpha particle or fission fragments is particularly significant, so that larger value of the applied voltage are required to these cause to achieve saturation. So to achieve the saturation, the larger the applied voltage are required. Okay, with electrons or gamma rays irradiation. Also, the effect of volume recombination are more important for higher intensity of the irradiation and thus higher ions current. Okay, as you can see illustrated in figure 5.4, which is this. Okay, so you can see this is 300 volt, this is 500 volt, this is 800, and this is 1000 volts. Okay, so as the potential increases, you can see the saturation point got decreased. The 100 voltage has the lowest value while the 300 voltage has the maximum. So as you increase the external applied potential, your ion pairs becomes low. Okay, okay, at saturation. Understood? Here is the percentage by which the measured current falls short of true saturation is seen to increase as a function of the measured in ion current. At the lower irradiation level, the density of ions and the electrons or negative ions is correspondingly low, which I mentioned. Thus, higher voltage are required at higher irradiation rate to approach the true saturation current ion. This is mentioned here. So we need high voltage are required to high irradiation rate to approach the true saturated ion current. Okay, so if you want to approach the true saturated ion current, you have to apply the most external voltage. Okay, this dependence is evident in the current voltage characterization as I mentioned you in the figure. Okay, this figure, x-axis is the ionization current in nanoamperes and y-axis is the recombination loss. Okay, okay, so the recombination loss is less for the more potential. Okay, if the production of ion pairs is uniform throughout the volume of an ion chamber, the drift of positive charge towards the cathode and negative charge towards the anode, which creates some imbalance in the steady state concentration of two charge carriers. Okay, so he is just saying that if your production of ion pairs are uniform in the ion chamber, then the positive charge towards the cathode moves and negative charge moves towards the anode. Okay, which moves an imbalance in the steady state concentration of the two charge carriers. The concentration of the positive ions will be greater near the cathode, as I mentioned, and the opposite, which is true for the negative charge. Wherever a gradient exists for a species that is free migrates, some diffusion must take place in the direction of decreasing concentration. Okay, the direction of diffusion is therefore opposite that of the charge carrier flow caused by the electric field, and the effect can be reduced by measured the ion current. From an analysis given by Rossi and Sturp, the perturbation is measured. Ion current is given by this relation. Okay, this is very important relation. You can find by using this formula. Okay, what this formula says that minus del I divided by I equals to epsilon kT divided by EV, whereas your epsilon is the ratio of the average energy of charge carrier with electric field, and whereas K is the Boltzmann, T capital T is the absolute temperature, small e is the electronic charge, and V is the applied voltage externally when you apply it with the gas chamber. So from this formula you can easily find the change in current. Okay, this minus del I by del T basically the, you can say that this is the relative change in current. Okay, this is the relative change in current, del I by del T. Okay, so let's suppose, let me give you a practical example, like you can solve it by yourself. A device operates at temperature 27 degrees Celsius with average electron energy 0.025 eV. If the applied voltage is 1 volt, calculate the relative change in current. So the value of average energy of electron is given, which is 0.025 eV, okay, which you have to put instead of this epsilon. K is the Boltzmann. You already know Boltzmann constant is equals to 1.3 into 10 raised to the power minus 23. Okay, this Boltzmann is equal to, let me write here, 1.3 multiplies by 10 raised to power minus 23. This is the Boltzmann constant Kb equals to, okay, and if the temperature, as I mentioned, is 27 Celsius, but you want in Kelvin, so you know that how you can convert from Celsius to Kelvin. Just add your Celsius value with 273. So 273 plus 27, which I told you in the problem, it becomes 300. So you have to multiply epsilon, which is 0.025, multiply by 1.3 into 10 raised to the power minus 23, which is the value of Boltzmann constant, multiply by 300, divided by E. E value, you know that electron charge, which is 1.6 into 10 raised to the minus 19, and V voltage is also mentioned in the problem, which I told you 1 volt. So after solving that problem, you will get your answer of the relative change in current, and that is equals to 6.4 into 10 raised to the power minus 4. Okay, so this is how you can solve the problems related to this relative change in current. So now move on towards the next topic. So first of all, there is a thing which you have to know, how that at room temperature, here is mentioned the factor Kt E by E. This is a factor Kt divided by E is approximately equals to 2.5 into 10 raised to the power minus 2 volts. So keep remember this thing. At room temperature, you know that room temperature is basically is 300 Kelvin. Okay, and voltage is given and the value of average energy is given. You can easily calculate the relative change in current. The only thing you have to know how is that at room temperature the factor is Kt by E is approximately equals to this, and for ions E is not much larger than unity. And for ions, your epsilon is not much larger than unity. As I mentioned you before in problem that your epsilon is equals to 0.025. And you know that 0.025 is smaller than 1. Okay, definitely. Now move on towards the next topic, which is the design and operation of DC ion chamber. So in this, what you have to do, you are going to use electrodes and you have to use gas with pressure, okay, to fast reaction. What it says basically, when an ion chamber is used in direct current mode, it is possible to collect the negative charge either as free electrons or as negative ions. So it's your choice. When an ion chamber is used in direct current and mode, so it is possible you can collect either the negative charges or either the free electrons, okay, or negative ions. Okay, you can collect the negative charges as per your concern. Free electrons, which are also negative, and negative ions, which are also negative. Therefore, virtually any filled gas can be used for chamber, including those that have high electron attachment coefficients. Although recombination is more significant when negative ions are formed, diffusion losses are less important. Okay. So this is how we will discuss about the design and operations of DC ion chambers. How you can design the ion chambers. Your DC means direct current mode chambers. Okay, not AC ion chambers. DC direct ion chambers. Okay. Although recombination is more significant when negative ions are formed, diffusion losses are less important. Conditions of saturation can normally be achieved over dimensions of a few centimeters using applied voltage that are no greater than 10 or 100 volts. Air is the most common filled gas and is one of which negative ions are readily formed. In air, you know that there are many negative ions. Air is required in those chambers designed for the measurement of gamma ray exposures. So you can use air in this type of chambers, in DC ion chambers, okay, for the measurement of the exposure of the gamma ray. Denser gases such as argon are sometimes chosen in other applications to increase the ionization density within the given volume. So denser gases like argon, these are used in other applications, not in this DC ion chambers. Why? Because this is used in other applications like to increase the ionization density within the given value. So if you want to increase the ionization density inside that chamber volume, so you will have to use argon. Okay. But for DC ion chambers, you can use the air. The filled gas pressure is often 1 atmosphere. Okay, so at atmospheric pressure, you have to use 1 atmospheric pressure. Although higher pressure are sometimes used to increase the sensitivity. Sometimes you use the higher pressure than 1 to increase the sensitivity. Okay, so this is how you can use to design the DC ion chambers. Now move on towards the next, which is about the measurements of ion current. So how you can measure the ion current? So simple is that you know that we have to measure the current. So you know that when we are using the simple circuit, we use the to find the current, we use the Ohm's law, which we know that which is V is equals to IR. Okay. So to find the current, we use the same expressions of Ohm's law. So the magnitude of ionization current under typical conditions is much too small to be measured using standard galvanometer techniques. Okay, so ionization current under typical condition is too much small to be measured using the standard galvanometer techniques. So you cannot measure your this current by the galvanometer. Okay, so what you have to use other than galvanometer, then instead some active amplification of the current must be carried out to allow its indirect measurement. So you can measure the gas ion chamber current indirectly. Okay, indirectly. An electrometer, an electrometer indirectly measure. So which electrometer? Okay, this is your meter which is measure the current indirectly. The current by sensing the voltage drop across a series resistance. Okay, voltage drop and series resistance means there is a relation of resistance R and there is a relation of voltage V, and you have to measure the current. So definitely you use the Ohm's law, which is V is equals to IR. Placed in the measurement circuit, the voltage developed across the resistor typically within a value of 10 to the power 9 to 10 to the power 12 ohms. This is the value of resistance. Can be amplified by serve as the basis of the Meyer signal. One weakness of standard electrometer circuits is that they must be DC coupled throughout. Okay, any small drift or gradual change in component values therefore results in corresponding change in the measurement output current. The circuits of this type must frequently be balanced by sorting the input and resetting the scale to zero. An alternative approach to convert the signal from DC to AC. So if you want to convert your signal from DC to AC, what you have to do, which then allows a more stable amplification of the AC signal in subsequent stage. This conversion is accomplished in the dynamic capacitor or vibrating reed electrometer by collecting the ion current across an RC circuit with long time constant as shown in figure. So you have to kind of find the current. So what you have to do, you have to use the Ohm's law, which is V equals to IR, where I is the steady current of the ionization current and Q is basically R is the resistance offered and V is the applied voltage. And you also know that your charge Q, which is stored inside the capacitance inside the capacitor, can be written as Q is equal to CV, which is the charge inside the capacitor. What you are going to do here, okay, you have to put the value of what you have to do here is that first of all you have to move this C, okay, this C to this side. So your V becomes equal to Q by C, and you have to multiply your whole expression by del C by C. So you see it becomes Q del C divided by C and C, so it becomes C square. And you have to put the value of Q here, okay, which is equal to CV. Once you put the value of QCV, one C cancels with this C, so you will only left with C, and you have to put the value of V, which is equal to IR, so it becomes IR divided by C del C. So here how you can find the voltage, IR del C by C. Okay, so this is how you can find the voltage. If you want to find the current, you have to use the same expression. Okay, now move on towards next, which is this radiation dose measurement with ion chambers. Okay, how you can measure the radiation dose within the ion chambers? Definitely, your ion chambers radiate some radiations, and if you measure those radiations, how you can measure? So first of all is the gamma ray exposure. So one of the most important application of ion chamber is the measurement of the gamma ray exposure. An air-filled ion chamber is particularly worse. As I mentioned you that you have to use air-filled ion chamber. Okay, so an air-filled ion chamber is particularly well suited for that application because the exposure is defined in terms of the amount of ionization charge created in air. Okay, under the proper conditions, a determination of the ionization charge in the air-filled ionization chamber can give an accurate measurement of the exposure, and a measurement of the ionization current will indicate the exposure rate. The task of measuring exposure is somewhat more complicated than it might first appear. because it is defined in terms of the ionization created by all the secondary electrons generated at the point at which the dose is to be measured. Strictly speaking, one would need to follow each of these secondary electrons over its entire range and measure all the ionization created along its tracks. Because the range in air of secondary electrons created by typical gamma ray emerge can be several meters. It is impractical to design an instrument that would carry out such a measurement directly. Instead, the principle of compensation is used. If the test volume of air is surrounded by an infinite sea of equivalent air that is also subjected to the same exposure over the course of the measurements, an exact compensation will occur were formed within the volume is exactly balanced by charge created within the test volume. So how you can find this exposure? Okay. So you have to use the air field. These are the ions. You can see one, two, three, four. This is the test volume you have to put inside and it measures the radiation dose. Okay, and these are the tracks you can see which it make inside your gas filled volume chamber. These are the radiation tracks. Okay, you can see how these tracks are formed between the two plates. Okay, so as I mentioned you, what is exposure here? So you can ask a question that what is exposure? So basically the charge produced per unit mass called exposure. Okay, the charge produced per unit mass is called the exposure. The charges which produced per unit mass, okay, of the radiation is called exposure, like gamma ray. Okay, so exposure rate is denoted by this R, and its unit is this coulomb per kg. Okay, coulomb is the unit of charge per unit mass, that's why coulomb per kg. And how you can measure this exposure rate? To find the radiation exposure, you have to use this formula, which is equals to R equals to Is divided by M, whereas I is the saturation ion current and M is the mass. Okay, air mass made of chamber volume and the density at STP, standard temperature pressure, whereas your M is equals to this 1.293 kg per meter cube volume P divided by P naught, which is at constant pressure, and T naught divided by T at the temperature, at standard temperature pressure. Okay, whereas this V is the volume inside your gas chamber, and whereas your only P is the air pressure within the chamber, and P naught is the standard pressure. And you know that standard pressure is 760 millimeter Hg, or you can say 1.013 into 10 to the power 5 pascals. And T is the uh, air temperature within the chamber, and T naught is the standard temperature, and you know that the standard temperature is 273.15 kelvins. So this is the formula of M. Okay, so to find the radiation exposure you need Is divided by M. Is, which is the saturation ionization current, divided by M, and M can be written as this 1.293 kg per meter cube volume P divided by P naught and T naught divided by T. Okay, so for that, let me give you an example. You can solve it by yourself. Let's suppose you have a volume of 1000 centimeter cube and you have a pressure of 850 millimeter Hg mercury, and your T naught and your temperature is basically, let me provide you. the temperature, and let's suppose your temperature is 23 degrees Celsius. Okay, you have to find what you have to find the mass. Okay, how you can find the mass? You know the expression is 1.29 multiplies by kg per meter cube. Okay, and multiplies by volume which I mentioned you, which is 1000, multiplied by p divided by p naught, p which is the temperature which I provide you, which is 850, divided by p naught, you know that is the standard temperature. You have to use it 760 because upside is the 850 mm per hg, and divided by 760 mm per hg, unit cancels, and remaining is T naught divided by T. The temperature I provide you in Celsius. You have to convert it in Kelvins because your T naught temperature, standard temperature, is also in Kelvins, which is 273.15 Kelvins, divided by your temperature, which I mentioned you 23 Celsius. 23 Celsius in Kelvins is 300, sorry, 296. So 237 divided 0.15 divided by 296, and multiply this all. 1.293 multiplied by 1000 multiplied by 850 divided by 760 multiplied by 273.15 divided by 300, you will get your answer of mass, and that's equals to 1334 kg per meter cube. Okay, so this is how you can solve the practical problems related to radiation exposure. Okay, gamma ray exposure. Now move on towards next, which is our last topic of today's lecture, which is about the absorbed dose. What is absorbed dose? So gas filled ionization chamber. So in gas filled ionization chamber, the energy absorbed per unit mass is called as the absorbed dose. Okay, the energy absorbed, as the name stands for absorbed, dose. So it has to be absorbed. So what absorbed? The energy absorbed per unit mass is known as the absorbed dose. So gas filled ionization chamber can also be applied indirectly to measure the absorbed dose, the energy absorbed per unit mass in arbitrary material. The technique is based on the applications of Bragg's-Gray principle. Okay, this is a principle which is used to measure the absorbed dose. Okay, Bragg's-Gray principle, which states that the absorbed dose, which can be denoted by dm, in a given material can be deduced from the ionization produced in the small gas-filled cavity within the material. Okay, and the expression of absorbed dose is this: your dm equals to WSMP, whereas your W is the average energy loss per ion pair, and Sm is basically the relative mass stopping power, energy loss per unit density of the material of the gas, and P is the number of ion pairs per unit mass formed in the gas. Okay, so this is how you can find the absorbed dose, which is according to the Bragg's-Gray principle, and the units of absorbed dose dm is joule per kg. Okay, and you can also say the unit of absorbed dose is grays, because this is by the scientist Bragg's-Gray. That's why the unit of absorbed dose can also be mentioned as gray. So the unit of absorbed dose is gray, and gray is joule per kg. And what is the unit of W, average energy loss per ion pair? Joule per ion pair. Okay, so the unit of SM is W is joule per ion pair. And what is the unit of P? Ion pair per kg. Understood? These are the units. So in order for the dose dm to be measured in grays, okay, so the dm to be measured in grays, which is joule per kg, and W can be expressed in joule per ion pairs, and P is measured in the pair ion pairs per kg. Okay, The cavity should be small compared to the range of the primary or secondary charged particles associated with the radiation so that its presence does not greatly affect the particle flux. In case of gamma rays, the solid medium should also be large compared with the range of the secondary electrons. So the electronic equilibrium is established at the inner walls of the cavity. Okay, so let me provide you a practical example for this topic. Then we will end our today's lecture. So let me give you another problem. You have to solve it by yourself using this formula. So the problem is an ionization chamber measures an ionization current corresponding to P equals to 1.6 into 10 raised to power minus 4 coulomb per kg. Okay. So the value of P is given, which is 1.6 into 10 raised to power minus 4 coulomb per kg in tissue. The average energy loss per ion pair is 34 eV. So the value of W is given. Energy loss per ion pair is 34 eV. And the stopping power of the medium is 2.5 into 10 raised to minus 2. Means the value of Sm is also given, which is 2.5 into 10 raised to minus 2. Calculate the absorbed dose. So what you have to do, you just have to multiply W by Sm into P. So the value of W is 34, but the value of uh, energy loss per ampere is in EV. We need in joules. So what we have to do? We have to multiply our by 1.6 into 10 raised to minus 19. So the value of W becomes 34 multiply 1.6 into 10 raised to minus 19. Okay. So the value of W is done. Multiply by value of Sm. What is the value of Sm? As I mentioned you, the value of Sm is 2.5 into 10 raised to minus 2. Okay. And the value of P is also given, which is 1.6 into 10 raised to minus 4. After calculating, after multiply this, you will get your value of absorbed dose, and your answer is 2.17 into 10 raised to power minus 23 joule per kg. Or you can also say it as grace. Dm equals to 2.17 into 10 raised to power minus 23 grace. So this is how you can measure the absorbed dose according to Bragg's-Gray principle. So that's all for today's lecture number 17 of principal methods and applications of nuclear tracks. In our coming video, we will discuss the applications of DC ion chambers. Till then, take care. Allah Hafiz.